Good morning and welcome to Inner West Council Library. We present an HSC lecture series in partnership with First Class Tutoring. But before all, I would like to acknowledge the traditional custodian of the land on which we produce this series, the Gadigal and Wangal people of the Eora Nation, and show my respect to their elders past, present and emerging, and to all First Australian watching this series with us. Enjoy and good luck for your exam after a very, very hard year.
Hello everyone, this is a Year 12 course review for the Mathematics Advanced course. In our first slide, we have a listing of all the topics that are studied in Year 12 as well as the subtopics. Whenever you see this paperclip icon, all that simply means is that within this topic that you are studying, there will be content that is common with the Mathematics Standard 2 as well as the content from the Mathematics Advanced course. At this point, I'd like to make mention that in Year 12, Year 11 Mathematics Advanced content becomes assumed knowledge. So when you are preparing for your trial exams as well as for your HSC exams, you will need to be familiar with a thorough understanding of both your Year 11 and also your Year 12 content. Okay, so 5 topics to go through. Each one will be themed a different colour in this slide, as we will see shortly. Let's start. Okay, so over to our first question, and what we have is a transformation question. Now, I'm just reminding you that there are 3 types of transformation. The first one is a translation. The second one is also called a reflection. And then the last one is called a dilation. Now, all of these 3 transformations can happen both in the x and also in the y axis. All right, let's start. So we have a graph of a function and we've been given its formula. Now straight away we need to recognize that it's going to be a hyperbolic function, because a hyperbolic function is in the form of a over x. All right, and what we also need to recognize is that this plus c here is my vertical translation, and this denominator over here accounts for my horizontal translation. Okay, so first question, what is the value of b? Well, remember x plus b cannot equal to 0, hence that's why we have this asymptote. Well, what's the equation of this asymptote? X is equal to -3. So if x is equal to -3, therefore b has to equal to 3, okay? If you substitute -3 here and 3 here, okay, you're going to get 0, and remember, x plus b cannot equal to 0, otherwise the function will not exist. Okay, so it's been translated 3 units to the left. Now C is a straightforward answer. This whole function has been moved 2 units down. Okay, explain why the value of A is a negative. So this is an explanation question, so a written response is what is required. Now, in the hyperbolic function, if the value of A is greater than 0, so that means that it's positive, the function will start, and that's important, will start, because remember it's been going through some translations, will start in the first and the third quadrants, right? Okay, this function has a value of a, which is negative, as it has undergone a reflection in the x-axis, and thus now starts in the second and fourth quadrants. Okay, prior to being translated. Okay, so I think that's a very, very thorough and an extensive answer. Okay, now the next type of transformations is mentioned in this question over here, and what we have is a dilation. Okay, so a dilation is a stretching. So you can stretch away from your x-axis. So you can stretch away from the x-axis, which will make this like that. Okay, so that's your x-axis dilation. Okay, by multiplying your whole function by a number. Let's choose a different color, or you can dilate from the y-axis. So stretch from the y-axis. Okay, by substituting x by a multiple of x. Now here it'll be by a factor. So let's add in by a factor of 1 over k. Alright, so that's the understanding behind it. Okay, over here, and just lastly, that's, oh sorry, look at that, not the same height. So the height was, everything will still be the same. Okay, except it's going to be stretched from the y-axis. Okay, so over here, so what substitutions would need to be made? Well, here the domain is getting halved. Okay, so therefore substitute 2x for x. Okay, and that would be a perfect answer. Or you can give the equation of the new function, which is, instead of f of x equals the square root of x, it'll be now the square root of 2x outside of, instead of 1 minus x, it'll be 1 minus 2x. Okay? Alright, in our third question, what we're having a look at is the inequalities. We're having a look at how we can describe this shaded region. Now there's two different responses that I will guide you guys through. First thing is, I'm going to choose this point over here, which is 1, 0, and what I'm going to do is substitute this point into both of the given equations, so into y equals x, and sub 1, 0 into y equals x squared minus 4x. Now what I would get over here is the left hand side. Well, the left hand side is y, so that's equal to 0. The right hand side, well, that's equal to x, so when I substitute 1, I'm going to get 1. So therefore the left hand side quite clearly is less than or equal to. Now why am I including equal to? Because this line is unbroken, the right hand side. So therefore y is less than or equal to x. Okay, let's do the same thing over here. Left hand side, well, that's y. I'm going to replace that with 0. The right hand side, 1 squared minus 4 times 1, which is negative 3. Okay, therefore the left hand side in this case is greater, and once again this function is unbroken or equal to the right hand side. So therefore y is greater or equal to x squared minus 4x. Now, Therefore, my answer is going to be y is less than or equal to x with the intersection of y is greater or equal to x squared minus 4x. Now that's a great answer, okay? Or the other way that you could do it is by having a look at what's happening here. Now, this region is in the domain from x is equal to 0 to x is equal to 5. So let's write that. In the domain of 0 to 5, and including 0 and 5. Now the domain only talks about x values, okay? This graph, y is equal to x, so x sits above this graph over here. Alright, so x is greater or equal to x squared minus 4x. And that is your alternate answer. Now, notice the theme change, the color change. So now we're moving from functions to trigonometric functions. Alright, so we've been given this function, y equals 5 sine of 2x minus 1. And so we've got a sine function, and then what we have is write down the value of the period. Now, I've seen lots of different formulas for periods. Sometimes they're given as L equals L for length. Sometimes they're given as T equals T for time. Okay? Alright. Either way, doesn't really matter. What you guys would need to recognize is that the period of a sine of x function is 2 pi. But here, I don't have sine of x, I've got sine of 2x. So I need to divide by the coefficient of x, okay, which is going to give me a period of pi. Now I'm going to link that back to our second question within our slide, that dilation. So remember, a dilation, okay, obviously here it's undergoing two dilations because I'm multiplying the function by a constant, and I'm also replacing x with a multiple of x, okay? So over here, it's being dilated away from the x-axis and also from the y-axis, but in this case, my period is pi. All right, so that's the answer for the first part. Now, write down, for the second part, write down the range using set notations or inequalities. Right. So let's see what actually happens here. So we need to build it up, right? So for the sine of x, okay, it oscillates between 1 and -1. Okay, sine of 2x, it'll still do the same. That's fine. Choose a different color. What happens if I put a 5? So that's that dilation once again. Okay. This time it's going to be away from the x-axis. So now that's going to take it up to 5 and then -5. Okay, so let's wipe the 1 and the -1. Okay, lastly, in black, I have -1. So that's that. Vertical translation. So now I'm going to dip it down by 1. So now it's going to be at 4. And then down to -6, okay? So get rid of the 5 and the -5, okay? So that's what's happening. That's what's happening in B. So what's the range? Well, using set notation, it's going to oscillate between -6, including 6, up to 4, and including 4. So that's how you do set notation. Okay, if you're asked to do it using inequalities, right, we're talking about our y values. Well, it's going to be less than 6 and greater than -4. Look, at this stage, I might mention that based on what we've been given from NESA and the sample papers, you'll probably need to be, be competent in set notation. Okay. All right. Lastly, it's now asking us to sketch this particular function, okay, in the domain of -y to -pi to +pi. Okay, So a couple of things. So 0 over here, when x is equal to 0, we start at -1. So that's really important, -1 over here. Remember, let's go again. Sorry guys, I just want to have enough space to actually fit it. Okay, so here is my y-axis, and we'll go x-axis that way. Okay, and you'll see why I've actually changed it. All right, so -1, then we go down to -6. Okay, and then we go up as high as -4. Okay, so all right, so that's my y-axis. This is my x-axis. So 0. What's my period? Well, my period is pi. So let's put pi over here and then go to -pi on this side. Halfway through the period is pi on 2. I'm actually going to write that over here, and you'll see why in a minute. Okay, because at pi on 2, I'm back to my midline. So this is where I start, and this is where I finish. Let's do the same markings on the other side. -pi on 2, going to be at -1. Where I finish is I'm also going to be at -1. Now, halfway between 0 and pi on 2 is pi on 4, and I'm going to be at my maximum turning point. So let's draw that. And then halfway between pi on 2 and pi, 3 pi on 4, I'm going to be at my minimum turning point, which is there, and then I end up there. Okay, let's do exactly the same markings on this side. So minimum turning point over here, maximum turning point over here. What are these points? -pi on 4 and -3 pi on 4. Perfect. Let's join everything together in one nice smooth curve. All right, and that's how you would sketch it. So make sure that you know where you're starting, where you are finishing. The period always divided by 2 first, and then by 4 just to get your important points on the actual trig function. All right, let's move on. Okay, so describe an appropriate sequence of transformation that will transform the graph of f of x equals cos of x into the graph of f of x equals cos of 2x minus pi on 2. In each step, you must describe the effect. Okay, so let's start, guys. So I've got f of x equals cos of x. That's what I've been given. So now for my first transformation, well, I'm going to substitute 2x over here. And what will I get? I'm going to get cos of 2x. Okay? So what's the effect? Okay? Because in each step, you must describe, okay, the effect. Okay? So here the effect is, well, I'm substituting 2x for x. So the period will be halved. The period will be halved to pi. All right. Okay, and once again, that links into with the previous question and also with question 2. Okay, then what happens next? Well, I do this. So now I substitute f of 2x minus pi on 2. Okay, and that's to give us cos of 2x minus pi on 2. Now here, it's all about the horizontal translation. So if I solve this to equal to 0, what I will get is pi on 4. So the horizontal translation is to the right to pi on 4 units. Okay. So describe an appropriate sequence of transformations that will transform the graph. In each step, you must describe the effect. Yeah, and I think I've done that well. All right. Alright, so probably the reason why I chose this as an interesting question is because a lot of people might have gotten the dilation, right? But then they might have made a mistake by saying that the translation is to pi on 2. It's actually to pi on 4, okay? And if you follow the working out. Look, I probably failed to mention this at the beginning, but at the beginning of each question, just try to pause the clip and try to work out your own solutions before you have a look at my guided solution. So over here we have a Ferris wheel. Sammy enters the capsule from the platform above. As you guys can see, the platform is raised a little bit from the ground. The Ferris wheel is rotating anti-clockwise, okay, going that way. The capsule attached to the Ferris wheel at point P, the height of P above the ground, H is modelled by this particular formula. Okay, well in this particular formula, so let's wipe all of that. In this particular formula, what we have is the amplitude is 55. Now some of you might say, well, the amplitude is negative 55. Look, either way, right? So a cosine graph looks like that. What we're doing is it's going to look like this, okay? Because the capsule is starting at the bottom, then it's going up in height, okay? So it's starting at the bottom, going up in height to its maximum height, which is over here, and then it's going back down, okay? Regardless, amplitude is 55. Remember, the amplitude is the distance away from its center. So distance is always a positive value, okay? And what else do we have? Well, we have the vertical translation. Of 65 up. Okay? So state the minimum heights. Well, the minimum height is going to be 65 minus 55, which is going to be 10 meters. So this distance over here is 10 meters, right? And then the maximum height, well, it's going to be 65 plus 55, which is 120 meters. All right, so that's the answer for the first one. Next one. How much time is Sam in the capsule? Now, look at our coefficient. Okay, so look at this function. Well, it's the height compared with time. Okay, so the period is in fact in form of t. So my time, well, it's a cosine function. So the period of a normal cosine function is 2 pi, and I'm going to be dividing it by the coefficient of t. Now put that into your calculator, you're going to get 30. Reread in the question, time is in minutes. Okay, Sammy can see the harbour bridge. Sammy can see the harbour bridge when he is 50 metres above in the air. So we're going to substitute 50 into this formula. So 50 equals 65 minus 55 cos of pi t on 15. Take away 65, and we're going to get negative 15 equals negative 55 cos of pi t on 15. Dividing both sides by negative 55, we're going to get cos of pi t on 15 equals, well, 15 divided by 55, or negative 15 divided by negative 55 is 3 on 11. Now I want to work out the value of t. So let's take the inverse cos of both sides, and we're going to get the inverse cos of pi t on 15 equals the inverse cos of 3 over 11. Now, when you put that into your calculator, please make sure that your calculator is set in radians. And a few things. This is not an exact value. Okay, so you'll need to use your calculator. And the last thing is that it's positive, so our answer is going to exist in the first and in the third quadrants. Now in the first quadrant, I'll be somewhere over here. Okay, this is 50 meters above the ground. And also over here, I'm also 50 meters above the ground. Alright, so let's continue. When I put this into my calculator, I'm going to get 1.29. And how do we measure, in my fourth quadrant, because cos is positive in the fourth quadrant. Now how do I measure angles in the fourth quadrant? Well, I measure it by doing 360 minus. Well, in this case, because it's radians, it's going to be 2 pi minus 1.29. So the two answers that I'm after is 1.29 and 4.99. Now that's pi t on 15. If I want to work out what t is equal to, I'm going to be multiplying both of these by 15 on pi. And the answer is going to be 6.16 minutes and 23.83 minutes. And that's your final answer. Okay, now our next slide is page 3 from the reference sheet. Page 3 from the reference sheet is split up into all the formulas that you guys would need to know in reference to differential calculus, and on the other side of it into integral calculus. Look, just before I start my next questions, I'm going to just give you an idea of just some things that you guys need. Quite obviously, these three formulas over here on the bottom, they are for E1 students, Extension 1 students. And the same as on the other side, these three formulas over here are for E1 students. Right, apart from that, all of these formulas come into play for us, but just a little bit of warning on the other side. And I just want to highlight these 4 formulas for integration. Now, when I teach the integral of, say, a sine function of x, this is what I teach. I teach that it's -1 over the derivative of this function multiplied by the cosine function of x plus c. Now, look what's been written over here. Look what's been provided over here. And it's the same as this formula over here. So when I teach the integral of an exponential function with a sine raised to a function of x, what I teach is that it's 1 over the derivative multiplied by e to the power of f of x plus c. But look what's been given here, right? Please note that f of x has been included into integral in the integral statement. That's sort of, look, it's exactly the same, but if you're going to be using these formulas that have been provided, then move the f dash of x down to your denominators. I just wanted to make mention of these. Everything else we actually use, all right? But just these 4 formulas, please be aware of them. I think they could have the potential to cause just a little bit of confusion. So please use the formula sheet. I think it's a wonderful resource, but also try to recall what has been presented to you by your teachers and also in your textbooks. So let's get a start now on our third topic, which is calculus. Okay, we start with this question. So y equals the log of e to the power of x plus 1 over e to the power of x minus 1. And we're asked to differentiate it. Well, before I differentiate it, I'm going to apply the index law. And the index law states that it's the log of the numerator minus the log of the denominator. Okay, now when you do that, the whole question just falls apart. So for the first one, it's going to be, my denominator is going to be e to the x plus 1, and when you differentiate a log function, the derivative goes up the derivative of the denominator goes on the numerator, so it's e to the x. And it's the same over here, e to the x over e to the x minus 1. Okay? Now, a show question, you need to start with what you've been given and then end up showing what they're asking you to show. So we're not quite there yet. So all I've done is I've just differentiated it. Now I must do a little bit more to get to what they're asking me to show. So I'm going to combine the denominators. That means for my first fraction, I've multiplied both the numerator and the denominator of my first fraction by e to the x minus 1. Okay, for my second fraction, I've multiplied both the numerator and the denominator by e to the x plus 1. Okay. Right, so let's expand the numerator. So e to the x multiplied by e to the x is e to the 2x. E to the x multiplied by negative 1 is negative e to the x. Negative e to the x multiplied by e to the x is negative e to the 2x. And negative e multiplied by 1 is negative e to the x. Down the bottom, I've got a binomial multiplied by its conjugate, which is going to give me a result which is the difference of two squares. So e to the power of x squared is e to the power of 2x minus 1 squared, which is 1. For my numerator, e to the power of 2x minus e to the power of 2x, they cancel each other, and I'm left with negative 2 e to the power of x over e to the power of 2x minus 1, which is what they've asked me to show. So nice little question, derivative of a log, but you must apply the index law, not the index laws, you must apply the log laws. Okay, so over here, what we have is the derivative of an exponential function, but what we have is a numerical base. Now, on my formula sheet, the one that I've showed you, right at the bottom of the left-hand column, you have this formula, and we need to apply it. So we have y equals a to the power of f of x. Okay, the derivative of it, dy dx, is going to be ln of a multiplied by f dash of x, and then a to the power of f of x. Rightio, so let's get a start. Y equals 3 to the power of 2x. Applying the given rule from my reference sheet, it's going to be the log of a, well, the numerical base is 3, multiplied by f of x, f dash of x, so the derivative of 2x is 2, multiplied by the numerical base, which is 3 to the power of f of x, which is 2x. Tidying that up, you will get 2, the log of 3. Okay, let's put that there, multiplied by 3 to the power of 2x. Look, good answer. Some other alternatives you could have had is the log of 9. Okay, so just moving the coefficient over here to make it an index. So 3 squared is 9. Multiplied by 3 to the power of 2x. Another alternative, so these are all. So another alternative, well, you could do this. So the log of 9 multiplied by 9 to the power of x, okay? So some nice alternatives, or you could have done this right at the start. So y equals 3 to the power of 2x, y equals to 9 to the power of x, and then applied the given formula, which is dy dx equals the log of 9. The derivative of x is 1, and 9 to the power of x, which is log of 9, and 9 to the power of x. Okay, so many different ways to get to what you're after. Look, maybe a harder slant on this might be to do something like this. So I might just show it to you, even though we're not asking you to do it. So imagine if I had, say, y equals, say, well, let's move away from 3. Let's go say 5 to the power of, say, 3x, plus 2, okay? Now, this is really 5 to the power of 3x multiplied by 5 squared, which is 25. 5 to the power of 3x, which is the same as 20, so I'm still in y, which is the same as 25. 5 to the power of x is 125. Okay, and now I'm actually ready to apply the given rule, okay? So, this 25 is a constant, stays, all right? There's no issues there, right? So, the log of the numerical base, so it's the log of 125, okay, multiplied by the derivative of the function of x, well in this case it's 1, multiplied by the numerical base 125 to the power of f of x, which is 1, so 25. Log of 125 multiplied by 125 to the power of x, something a little bit harder. It's still doable based on the application of what we've been given in the reference sheet. So look, not a bad question to highlight here, okay? Let's move on. Okay, so our next question is an application of the derivative, and this is what we have is an optimization question, and in this case we're after the minimum. All right, look, when you read this question, what we have is that she starts off with a rectangular piece of steel. She bends the steel to make an open cylinder, and then she welds that section. She then welds this cylinder down to the circular base, all right? And the first question is asking us, what is the length of the weld, L? So L equals the height plus the circumference. So the height plus 2 pi r. I'm nearly there. I've got the 2 pi r part, but I need to somehow link the height to 8,000 over pi r squared. Well, what else have I been given? I've been given the volume, which is pi r squared h. And I've been given the volume is 8,000 cubic centimeters. All right, and there's my link. I'm going to divide both sides by pi r squared. H is equal to 8,000 over pi r squared. There's my link, and now I'm just going to substitute that in there. Okay, so sub into L equals H plus 2 pi r. So 8,000 over pi r squared plus 2 pi r. Alright, so now the beauty about this question, and this is an exam question, the beauty about this question is that if you were not able to get that, then you use part 1 in part 2. Okay, now that's a good exam question, okay? So it's not going to, it's going to allow you entry points at each part, okay? So let us now start part 2. And what I might do is I might wipe all of my working out, okay, because part 2 is actually quite significant in terms of the working out. Alright, so I'm going to start at L equals 8,000 over pi r squared plus 2 pi r. Okay, before I differentiate, so it's 8,000 pi r to the negative 2 plus 2 pi r. And now let's differentiate. So dl over dr, we're differentiating with respect to r. Now the 8,000 stays as it is, that's a constant. Okay, and I'm multiplying that by, okay, drop the power, and then less 1 for the power. Okay, and here it's 2 pi. Okay, 8,000 multiplied by negative 2 is negative 16,000 pi r cubed at the bottom plus 2 pi. Now, I want to solve for 0, so let dl dr equals to 0. And let's see where that ends up, where we end up. So let's take the negative 16,000 over pi r cubed to the other side, becomes positive. We'll cross multiply, so 2 pi squared r cubed equals 16,000. R is going to be the cube root of 16,000 over 2 pi squared. Now put that into your calculator and you are going to get 9.32. Alright, what I want to do next is I want to test that to see if it's a minimum. So 9.32 is there. One value above 9.32 is 10 and one value below it is 9. And when I substitute 9.32 into dl/dr, which is, I'll just highlight it here for you, which is there. Alright, when I substitute 9.32 into dl/dr, of course I'm going to get 0, right? So I've got a horizontal gradient. When I substitute 9, I'm going to get negative 0.7. So I'm going to get a decreasing gradient. Now at this stage, I must state that you must include the numerical substitutions. Just doing these is not on. Okay, you must justify your final answer based on calculations. So when I substitute 10, I'm going to get 1.19. Now that's a positive gradient which is increasing. Right, now based on these, I can summarize to say that therefore I've got a minimum at r is equal to 9.32, okay, which is what the question is asking me. Lastly, I need to find the value of h. So h is equal to 8,000 over pi r squared. I got that from part 1, by the way. Okay, so if you have a look, go back and have a look at the solution for part 1 that I wrote previously. Okay, so 8,000 divided by pi outside of 9.32 squared. Okay, and that's going to give us a value of 29.32, okay, centimeters. And that's the whole question answered. Look, just a word of advice once again, when you think you've got a solution, always go back and reread what the question is asking you and see if you have answered everything that they're asking. Calculate the length of r, there it is there. Okay, make sure that it's a minimum. There's my justifications for minimum there. And the value of h, and there's the value of h. Okay, so fantastic question there, and always make sure you reread the question to see if you've answered all parts of it before you move on. So now we move on to the other part of calculus, which is integral calculus. And let's have a look at this question over here, which is all to do with the antiderivative. So you've been asked to calculate f of x, and you have been given f dash of x. So the link there is that f of x is the integral of f dash of x with respects to dx, with respects to x. So what I'm really after here, guys, is the integral of x over x squared plus 9 with respects to x. Now I'm very close to an integral that's going to lead me to a log function. However, the numerator is not quite the derivative of the denominator. So what's the derivative of the denominator? Derivative of x squared is 2x. I don't have 2x, I've got x. So I'm going to manipulate by a factor of 2, and therefore outside of the integral sign, I'm going to manipulate by a factor of a half. Now, f of x, now I can integrate, is going to be half the log of, okay, the absolute value of x squared plus 9 plus c. So that's f of x. And now what I'm going to do is I'm going to substitute x is equal to 0 and f of x equals a log of 3. So the log of 3 equals half the log of, well, 0 plus 9 is just 9, okay? Plus c. Okay, using my log laws, I'm going to restate this as log of 9 to the power of a half, okay, which is the square root of 9, which is the log of 3. Okay, now taking the log of 3 away from both sides, so therefore c is equal to 0, so therefore my final answer, f of x, equals half the log of x squared plus 9. The absolute value of x squared plus 9. Okay, here we go. Okay, the next question, we've been asked to differentiate sine of 5x. Okay, now that's the same as sine to the power of 5 of x, and that's the same as the sine of x raised to the power of 5. So using the chain rule, drop the power, less 1 for the power, and then multiply by the derivative of the inside. Tidying that up, that's a good answer by the way. Tidying that up, we're going to get 5 sine to the power of 4x multiplied by the cos of x. Now we're being asked, well, what's the integral of sine to the power of 4 of x cos of x with respect to x? Now I know, based on this, that the integral of that is going to lead me to sine to the power of 5x. Now I don't have, in this statement, I don't have 5 sine to the power of 4x cos of x. But I can manipulate, so I'm going to put the 5 there, and therefore I would need to put the reciprocal outside of the integral, okay, sine. And so now I can actually integrate this to get to that, but I'm also multiplying it by a factor of 1 over 5. So it's 1 over 5 sine to the power of 5x plus c, okay? Final answer, or if you want, you can choose to move the sine to the power of 5x to the numerator and then put that over 5. That's fine, either way. So now over to my next question, and it's an interesting one which links up a number of topics together. So very, very quickly, what we have is the graph of y equals e to the power of x, which is there. And then the other one links us back to our first topic, which is functions. The other one looks like what's happening here. Well, I've got a reflection, I have a dilation, and also I have a vertical translation. Okay, so I thought that was a nice question to present to you guys. Okay, by the way, this is one over here. Now the next one I've got a vertical translation of 2. Okay, it's been reflected, so it's going to be a decaying function, and then the amplitude, so it's been multiplied by a factor of 3. So in other words, for this function over here, okay, if it was simply e to the power of negative x, the y-intercept would have been 1, multiplied that by 3, now it's now up to 3, then adding 2, it's now up to 5. Okay, so this function in blue is going to be something like this, and this is p. Alright, so now it's asking us, we'll find the coordinates of p. Alright, so I might just move all of that over here just to allow me a little bit of working space, alright, because I know that it's going to be a bit of a substantial solution. So what I'm going to do is I'm going to solve by substitution. So solve by substitution. So let's do that. E to the power of x equals 2 plus 3e to the negative x. E to the power of x equals 2 plus, well, using my knowledge of index laws, that's going to be over e to the power of x. Multiply everything by e to the power of x. Okay, we're going to get e to the power of 2x equals 2e to the power of x plus 3. Move everything to one side. E to the power of 2x minus 2e to the power of x minus 3 equals to 0. Now at this stage you need to recognize that this is going to be an equation which is going to be reducible to a quadratic. So if you make this simple substitution, what you will see is that you will end up with m squared minus 2m minus 3 is equal to 0, which we can factorize m minus 3 and m plus 1. When we solve, we're going to get m is equal to 3 and m is equal to negative 1. Now we sub back, m is equal to e to the power of x. So now instead of m, I'm going to substitute e to the power of x is equal to 3. And e to the power of x is equal to negative 1. Now guys, over here you need to say NA. You need to follow it with a statement. So you could say, well, e to the power of x exists above the x-axis, or you can't take the log of a negative. I think both are very nicely stated answers. And over here, well, you need to take the log of both sides, so you're going to get x is equal to the log of 3. Alright, so therefore y would equal to e to the power of x, and x is equal to the log of 3, so y will equal to 3. So we're just substituting for the value of y, so therefore p is the log of 3 and 3. Now that's a nice long solution over here, okay, and it's involving lots of previous topics. All right, now if these curves cut the y-axis at point A and B respectively, so A, B, okay, calculate the area bounded by AB and the arc AP and BP. All right, so we want this whole area over here. Now when you look at it, when you first look at it, you'd think that this is a question about area and the y-axis. However, the issue with that is that you would need to make x the subject of both of these formulas. Okay, so y equals e to the power of x, so therefore x is equal to the log of y. And the issue here is that you cannot integrate any log functions. Like, this is not within the scope of our course. Okay, so that's undoable. So now what we're going to do is we're going to do this with the area between two, the region between two curves. Okay, and we're going to be integrating with respects to x. Okay, now over here, just reminding you that this is ln of 3. So this is the area. Area is going to be the integral from 0 to the log of 3. Okay, now what's the top curve? The curve that lies on top? Well, it's 2 plus 3e to the negative x. And then I'm subtracting from it the function that lies on the bottom, which is e to the power of x. Okay, and I'm integrating all of that, okay, with respects to x. All right, so let's do that. What's the integral of 2 to x? Okay, plus the integral of 3 to the power of is 3e to the power of negative x. Well, that's 3. Dividing it by negative 1, multiplying it by e to the power of negative x. Okay? And the integral of e to the power of x, well, it's e to the power of x over 1. That's fine. I can do it over 1. I'm not. Okay? Because dividing by 1 is the same thing. And then all of that is from the log of 3 to 0. Okay. Let's tidy that up before we make our substitution. Okay, so I'm going to have 2x minus 3 over e to the power of x minus e to the power of x from 0 to the log of 3. Let's substitute now. So I'm going to get 2 the log of 3 minus 3 over e to the log of 3 minus e to the log of 3. Okay, then minus 2 times 0 is 0, minus 3 over e to the power of 0 minus e to the power of 0. Okay, very, very quickly, e to the power of log of 3, that's just going to give us 3. Okay, so I've got 2 log of 3 minus 3 over 3, which is 1, minus 3. Okay, minus 0 e to the power of 0 is 1. So 3 over 1 is 3. And then minus 1. Okay. Now, 2 log of 3 is the log of 9. Okay, so just moving it as a power. Here I'm going to get negative 4. And then here I'm going to get negative 4 as well. 2 negatives will give you a plus. So log of 9 minus 4 plus 4 leaves you with the log of 9 units squared. That's your final answer. So a really, really nice little question there. Alright, so now we move on to financial mathematics, and what we have is, our understanding of series and sequences. Could I please make mention that both for arithmetic and for geometric series, your formulas are given, as well as the sum to infinity formula is given. So please make sure that you use your reference sheet. Okay, so over here in the first one, I've got the log of 4, the log of 8, the log of 16, and then the log of 32. Okay, and then I want to prove that it's arithmetic. Well, just before I do that, so the log of 4 is actually, the log of 4 is actually 2 squared. Okay, the log of 8 is 2 cubed. The log of 16 is 2 to the power of 4, okay, and then the log of 32 is 2 to the power of 5. Okay, so I made that link once I saw these numbers. Okay, I made that link straight away, all right, that they are all related to the base of 2. Now, using my log laws, this is 2 log of 2, this is 3 log of 2, this is 4 log of 2, okay, and obviously 5 log of 2, and then so on and so on, okay? So prove that it's arithmetic. Well, to prove that it's arithmetic, my difference has to be consistent. So it's T3 minus T2, and that has to be the same as T2 minus T1, okay? So 2, 3, 4 log of 2 minus 2, 2, which is 3 log of 2. Is that the same as 3 log of 2 minus 2 log of 2? And I go, well, yeah, they are. Sorry, 2, 2, 2. They're not bases, they're actually numbers. Well, yes, they are. They are all equal to the log of 2. So I do have a common difference, and hence it is arithmetic. So common difference hence arithmetic. Okay, now find the sum of the first 8 terms. Well, I've been given n is equal to 8. I know that I've got my first term is 2 log of 2, and my common difference is just the log of 2. Okay, now using your formula that's given to you on your formula sheet, it's n over 2 outside of 2a plus n minus 1d. Okay, so the sum of the first 8 terms is 4 outside of 2 times 2 log of 2 plus 8 minus 1 is 7. 7 multiplied by the log of 2. Okay, so 4 lots of 2 multiplied by the 2 log of 2 is 4. Log of 2 plus 7 log of 2 is 11. The log of 2, okay, which will give you 44 the log of 2. And that's it. That's your final answer. So a nice little question there. All right. Now, with our next slide, so this one is, okay, so a patient is given 10 milliliters of a particular drug. During each of these 8-hour periods, the patient's body partially breaks down the drug. Only 1/3 of the total amount of the drug present in the patient's body at the beginning of each hour remains at the end of that period. Okay, so a lot of wording over here, but essentially how much of the drug is in the patient's body after the second dose is given? Well, when the first dose is given, only 1/3 of it remains. All right, and then after 8 hours, you are then given a further 10 mils. All right, so therefore, what we're going to have is 13.3 milliliters. Okay, that's it. All right, show that the total amount of the drug in a patient's body never exceeds 10 mils. Okay, so you're given 10, then you're given another 10, and in the patient's body, okay, you retain 1/3. Okay, you keep on retaining 1/3. Sorry, 27. Okay, and so on and so on. What we have here is a GP, and the first term is 10. The ratio is 1/3. Now the ratio is less than 1, so therefore what we want is our sum to infinity. Okay, so we put that into the formula. 10 divided by 2/3, and that's going to give us 15 milliliters. That means that it's never going to exceed 15 milliliters. All right. Alright, and so now we start with our financial mathematics, and what we're going to do here is we're going to use the recurring relationship. Okay, so Chris started a new job. 500 was deposited into a superannuation fund at the beginning of each month, and the money is invested at 0.5% per month, compounded monthly. Okay, so I'm going to start off with this. Now, these are very long solutions, guys, so please bear with me, okay? Let AN equal the amount at the end of each month. Okay, guys, so therefore A1, the amount at the end of the first month, well, his deposit is $500, and he's going to be getting 0.5%. Now, 0.5% equals 0.005. Okay, so put that into the compound interest formula, and we're going to get 1.005. Okay, so that's the amount of money that he's got at the end of the first month. Now, at the end of the second month, well, whatever he's got at the end of the first month is going to be compounded, plus the new $500 that he puts in at the beginning of the second month is also going to be compounded as well. All right. Now, A1 is 500 multiplied by 0.005. When I multiply it by a further 1.005, I'm going to get that squared. And this is the amount that he puts in at the beginning of the second month and what it accumulates to at the end of the second month. Now, A3, and you only need to do this 3 times, is the same as A2, which is this whole statement over here. And I'm going to be multiplying it by 1.005 once again, and then I'm going to, once again, add a further $500, which at the end of that third month will have accrued interest. So what I've underlined there in red, I'm going to multiply it by 1.005. Okay, so that becomes cubed. This one becomes squared, and then this over here, I'm just simply writing it over here. Now what I've got here is a pattern, and this pattern, if I take 500 out of it and then reverse the order, I've got 1.005 plus 1.005 squared plus 1.005 cubed. Okay. So I've got a geometric progression over here, okay? And I'm going to continue now this pattern all the way down to 240, okay? So at 240, this is what I will get based on this pattern. 500 outside of 1.005 plus 1.005 squared plus 1.005 cubed. Now remember, you need to have a minimum of 3 terms, okay? For you to have a geometric, progression, okay, and then we do the dot all the way up to 240, okay. So what I have is that after 240 months, I've got 500 multiplied by the sum of a GP, which is A outside of R to the power of n minus 1 over R minus 1, where A, okay, equals 1.005, R equals 1.005, and N is 240. So we put all of that now into our formula, and hopefully we can get this figure over here. So let's go. 1.005 outside of 1.005 to the power of 240 minus 1, all of that over 1.005 minus 1, which is 0.005. And put that into your calculator. You should get 232,175.55, okay, which equals to P. Fantastic answer, all right? So quite a bit of work to lead to that particular answer. Now that was part 1, and this will be part 2. So I need you guys just to remember that P equals 232,175.55, okay? So we might just write that right at the beginning. P equals 232,175.55. Okay, just checking that. Perfect. All right. So now, after retirement Chris withdraws $2,000 from the account at the end of each month. So he looks like he's self-funding his retirement without making any further deposits. The account continues to earn interest at 0.5% per month. Let AN be the amount left in the account after n month. Okay, so it's telling us what AN is, rightio. So now we will start. We don't need to make that summary statement at the beginning. So now we'll need to start with what's happening at the end of the first month. He's got his money, P, which is earning 0.5%, but then he makes a withdrawal of $2,000. Okay, so that's what's happening there. All right, now in the second month, well, it's whatever he's got in the first month, and there it is written there. Okay, well, it's going to earn interest, and then he makes another withdrawal. So let's substitute A1 into here. So it's going to be P 1.005 multiplied by 1.005, which will give us 1.005 squared, so that's for A2, minus 2,000 multiplied by 1.005, and then minus this new 2,000, okay? So all of that is A1. Okay, A1 multiplied by 1.005. And this is linked up to that. Okay? One more time, guys. A3. Well, it's whatever he's got in A2. That's right. He's going to earn interest on it. And then he's going to make a further $2,000 withdrawal. So now we take this statement here in A2 and we multiply everything by 1.005. So P to the power of 1.005 to the power of 3 minus 2,000, 1.005 squared minus 2,000, 1.005, and then this 2,000, we bring it down here. Now we have a pattern. I've established a pattern. So A3 is P to the power of 1.005 to the power of 3. Now I'm going to take out a factor of negative 2,000, and what I will have is, and then reverse the order, so what I will have is 1 outside of 1.005 and 1.005 squared. Now that's going to give me, once again, a GP where A is equal to 1, R is equal to 1.005, okay, and N, well, we'll see what N is equal to. Let's go all the way up to AN. So AN, let's continue this pattern, will be P to the power of 1.005 to the power of N. Because look, when it was 3, that was 3. When it was 2, this was 2, okay? Minus 2,000 outside of 1 plus 1.005 plus 1.005 squared, and all the way up to, and you need to show this, guys, you can't go from 3 all the way down to this answer. You haven't really showed anything. 0.005 to the power of n minus 1, okay? That's important to show that, because look, when it was A3, the highest power was 2, okay? Now, therefore, what you now need to say is you've got a GP, A is equal to 1, R is equal to 1.005, and N is equal to N. Right, so now, therefore, AN is P 1.005 to the power of N minus 2,000 multiplied by the sum of a geometrical progression, which is A1 outside of R to the power of N minus 1 over 0.005. Okay. All right, nearly there, and I'm running out of space, but hopefully, let's see how it works. Now, 2,000 divided by 0.05 gives me 400,000. Now, when you do that, you'll see the link there, all right? But still a while to go. 1.005n minus 1. Okay, expand that. P to the power of 1.005 to the power of n minus 400,000, 1, 2, 3, 4, multiplied by 1.005 to the power of n plus 400,000. Okay, take out 1.005 as a factor, 1.005 to the power of n as a factor. That will leave you with p minus 400,000, 1, 2, 3, 4, 5, okay, plus the 400,000, which is exactly what was requested, as requested. Okay, that's it. You've done it. Now for the last bit, part 2. For how many months will after retirement will there be money in the bank? So what we're now going to be doing is we are going to be substituting n is equal to 0. So we've got 0 is equal to, and we're also going to be substituting p is equal to 232,175 and 55 cents. Okay, so what we now are going to be solving is this equation. 0 equals 232,175 and 55 cents minus 400,000 multiplied by 1.005 to the power of n plus 400,000. All right. So 0 equals negative 167,824.55 multiplied by 1.005 to the power of n plus 400,000. Okay. And I'm trying to fit everything on the same page. Now what we'll do is we'll move this to the other side, then divide by that. Okay, so 1.005 to the power of n equals 400,000 divided by 167,824 and 55 cents. 1.005 to the power of n is going to give us 2.38, blah, blah, blah. Take the log of both sides. So therefore, n is equal to the log of 2.38, blah, 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 all over the log of 1.005. And we get n is equal to 174 months, which is the correct solution. Look, I hope you guys can make a little bit of sense out of this. It's definitely a lot of work to fit in onto one slide. So obviously, in an exam, your working out would need to be more spread out. Okay, last topic, and we're nearly there, guys. So the last topic, we're having a look at our statistical analysis. Okay, and what we have here is the length of time, x minutes. Now, straight away, when I read that, length of time, I need to ensure that this is going to be continuous. Okay, so this is a continuous variable. X is a continuous variable. Okay, and it also mentions that it's a probability density function. Okay, so find the probability. Okay, so find the probability. Now, to calculate probability, probability is area under the function, under the curve. Oh, it might help us out just to actually sketch this. Okay, so when I sketch this particular function, all right, I'm going to have a function that looks like this. Okay. And what I want is more than 8. So this is obviously x. So what I want is this area over here. Now, because this function goes all the way up to infinity, okay, All right, what I'm going to do is that the probability that x is greater or equal to 8, well, it's going to be equal to 1 minus the integral from 0 to 8. So I'm going to calculate this area over here, all right? And then by taking away 1, because we know that the area under the probability density function is always equal to 1, okay? That will allow me to calculate the area under the curve from 8 onwards. Okay, so let's do that. So it's the integral of, well, it's 1/5. I'm going to take that out because that's a constant, right? E to the power of negative x on 5 with respect to dx. So it's going to be 1 minus a fifth multiplied by e to the power of negative x on 5. What's the derivative of that? Well, it's negative a fifth, okay, and I need to calculate the area from 0 to 8. So that's going to give us 1 minus a fifth outside of 1 divided by negative a fifth is negative 5 e to the power of negative x on 5 from 8 to 0, which will give us 1 minus, now a fifth multiplied, negative a fifth multiplied by negative 5, well, that's going to give us plus 1, okay, so plus e to the power of negative x on 5 from 0 to 8. Let's substitute 1 plus e to the power of negative 8 on 5 minus e to the power of, well, it's going to be 0, 1 plus e to the power of negative 8 on 5 minus 1, which is e to the power of negative 8 on 5, and that's the probability of it. Okay, so that's this area over here, greater than 5. Okay, so a nice little problem. Now, when we read our next question, we have, well, what's the probability that it's going to be, find that more than 12 minutes elapsed between successive time given that. See this given that? That's what we have, conditional probability. So when we write our statement, so the probability of x is greater than 12, okay, given that x is greater than 8, all right? Well, that's going to be the probability that x is greater than 12 with the intersection of x is greater than 8 over the probability that x is greater than 8. Now, where am I getting all of this from? The formula is supplied on the formula sheet. Okay, let's go back to my diagram. Now, this is the area of x is greater than 8, and if I do now in black the area that x is greater than 12, it's this area over here. Now, where do they intersect? Well, they intersect at the area that is greater than 12. So all I'm after is the area that is greater than 12 over the probability that x is greater than 8, which I've actually worked out in the first part of this question. Now, if I want to calculate the probability that x is greater than 12, I'm going to do exactly the same thing. So the probability that x is greater than 12, or even equal to greater than 12, okay, there's no difference between the signs over here. It's actually going to be exactly the same working out. So it's going to be 1 minus a fifth, so I'm going to be calculating this area over here of the integral of e to the power of negative x on 5 with respect to x from 0 to 12. And the working out will be exactly the same, and my answer is going to be negative e to the negative 12 on 5. So e to the negative 12 on 5 over e to the negative 8 on 5. Okay, using index laws, I've got the same base, so therefore I take away negative 12 minus negative 8. Well, that's going to give you negative 4. Okay, great answer, or 0.4493. Okay, so a really nice question which brings in some, year 11 content as well as, the current year 12 content. Okay. Last slide, everyone. Okay, so what we have here is a probability density function. Okay, so straight away try to sketch this. Okay, so what we have from 0 to 2, we have a quadratic. Now when I substitute 2 into here, I'm going to get 3 over 8. Okay, and when I substitute 2 into here, I'm also going to get 3 over 8. And that's nice because what we now have is, so this is at 2 and this is at 6, and obviously this is 0. So this is the sketch of my probability density function. Now it says otherwise it's 0, so you also need to indicate that and this over here. Okay, now that's a perfect sketch of your density function. Okay, so done. Okay, now if the probability from 2 to 6 is 3/4, okay, so let's make a little bit of sense here. So so it's given us the probability, so it's actually given us the area underneath this function. So the area underneath this function, okay, is 0.75. Now I can actually work that out. It wouldn't have been hard to work that out. It's a triangle, half the base times the height. Well, the base is 4 and the height is 3/8. And if you do that, it's going to be 3/4, yeah? All right? Okay, so but what it's telling us is that if the area underneath, if the area from 2 to 6, is 0.75, write down 2 statistical measures to describe x is equal to 2. Now look at x is equal to 2 over here. We've got our peak. So therefore, one way to describe this point is the mode. Now the other way to describe this mode, well, the area on this side is going to be 0.25, so therefore it's my Q1, my lower quartile. Q1. Right. Now what we're after is find the median. So we want the value of x, okay, that represents the median. Now we know from here to 2 is 0.25. So remember the median is the area under the graph that equals 0.5. Okay, so the area, okay, from, well, we've already got the area from 0 to 2. That's 0.25. So what we now know is that the area of the other side, which is from 2 to 6, but we want to know the value of x, right? So the area, so it's going to be somewhere over here. Our median is going to be somewhere over here, x. All right. So we want the integral from 2 to x of 3 over 32. Well, that's a constant, so let's put that out over here. We want the integral of 6 minus x with respects to x, and for all of that to equal to 0.5, okay? So not a bad little problem there. Let's take away 0.25 over here. And so what we have is 3 over 32 multiplied by the integral of 6 minus x from 2 to x to equal to 0.25. Okay, let's integrate. And so the integral of 6 is 6x. And the integral of x is x squared on 2. Okay. Let's substitute x and 2. And let's also multiply 0.25 by 32 on 3. Alright, let's solve it. So when I substitute x, I'm going to get 6x minus x squared minus 2. And then when I substitute 2, I'm going to get 12 minus 2. Okay, equals, and then on the other side, I'm going to get 2.8 over 3. Okay, so now I've got 6x minus x squared on 2 minus 10 equals 8 on 3. Okay, let's multiply everything by 6, and what I will get is 36x minus 3x squared minus 60 equals to 16. Okay, so you can see the solution there forming for us. Negative 3x squared plus 36x minus 76 is equal to 0. Let's change everything to the other side. So 3x squared minus 36x plus 76 is equal to 0. Okay, and let's use the quadratic formula, and what we will get is these two values, right? So let's have a quick look. So we're going to get x is equal to 36 plus the square root of 384 over 6. And we're also going to get 36 minus the square root of 384 over 6. Now let's go to red. This answer over here is 9.26. Okay, now that's not applicable because my range only goes up to, so let's bring it over here. So x equals 9.26. Okay, now that's an NA. I have to reject that as PDF. Well, as the probability would equal to 0 over here. Probability equals to 0, okay? And now this answer over here, 2.73, and that's your median, alright? So let's write this one over here, 2.73, that's my median, alright? Now the last one is all in relations to the mean of this PDF. Ooh, let's try to fit it in over here. Alright, now the mean of the PDF. Well, we know that the mean from the formula sheet is given to us as x f of x. Okay, now we apply that to discrete data, but we can also apply it to continuous data over here as well. So guys, the mean is going to be the integral from 0 to 2 of x, f of x, which is 3 on 32 x squared dx, plus the integral from 2 to 6 of x multiplied by f of x, which is 3 on 32 6 minus x dx. Alright. Now I wish I could keep all of this for you guys, but unfortunately this is a long solution, so I actually need to use all of this space. Alright, nearly done. So over here, what we're going to do is we're going to take the 3 over 32, because that's a constant, down to the front, and we're after the integral from 0 to 2. Well, x multiplied by x squared is x cubed. That's an easy one. We're going to do exactly the same thing over here. 3 over 32, we're going to take it down to the front of our integral. So from 2 to 6. X multiplied by 6 is 6x. X multiplied by negative x is negative x squared. So that's what we're actually integrating. All right, let's do it. So 3 over 32, and we're after the integral of x cubed. So it's x to the power of 4 on 4. And we're going from 0 to 2. All right, plus 3 over 32 multiplied by the integral of 6x, which is 6x squared on 2. So let's go 3x squared. And the integral of x squared is x cubed on 3. Now this integral, we're taking it from 2 to 6. All right, now it's just a matter of substitution. So it's 3 over 32. Now substituting 2 to the power of 4 on 4, so that's going to give us 4, okay, minus 0, okay, plus 3 on 32 outside of 3 multiplied by 6 squared, which is 36. 6 cubed is 216. Minus 3 multiplied by 2 squared, that's 3 times 4, okay, minus 8 on 3. Okay, 3 on 32 outside of 16 divided by 4 is 4. Okay, plus 3 on 32. And then over here, what we're going to get, when you put all of that into your calculator, it's going to be 80 on 3. Okay, evaluate both of these, you're going to get mu is equal to 2.875. All right. So that's the end of our presentation. Just want to encourage everyone that watches this video to please practice as much as you can and to go in really well prepared for both your trial exams and also your HSC. Now, the best advice that I can give all candidates is that your HSC mark accounts for half of your overall mark, so you do not give up learning and practicing the content of this course until the last minute before you go into your exam to sit for your advanced HSC paper. Good luck, everyone.